Welcome to a tutorial on the memory chips and expansion. Alright, so in this tutorial video we're going to have a word about memory chips. Okay, so the memory chips that I'm going to talk about here, okay, are some examples of real-life memory chips that we frequently use in microprocessor oriented systems. So these memory chips that I'm going to talk about, you need to connect them externally to your microprocessor, 8085 microprocessor, in order to provide it with sufficient memory support. So these chips that I'm going to talk about here are basically referred to as RAM, or random access memory. So they just perform this particular function. Okay, so let's just start with the example of a 2 KB chip. Okay, a 2 kilobyte memory chip. Okay, also referred to its name is basically referred to as well IDT 6116 CMOS RAM chip. Okay, or rather more precisely, it's a CMOS static RAM. So I'm going to write here SRAM chip. All right, now this chip basically has a total of 24 pins. So the number of pins on this chip is basically equal to 24, and these pins can be divided into two categories. So one is basically the input output and the address lines, okay, and the other one are basically referred to as control lines. So all these lines, the total number of lines or pins coming under the input output and address lines and the control lines would make the total of 24 pins on this particular chip. Now but before going into these details, let me just revisit what I just left out over here. So this chip is basically more precisely referred to as a 2K by 8 chip. Okay, so here this second number, that is 8, well, this refers to that refers to the fact that this memory chip has an array of 8-bit registers inside. Okay, so this particular memory chip contains an array of 8-bit registers. Okay, so registers that basically store 8-bit binary words, and the first number, that is 2K, here basically refers to the number, or rather the total number of registers present inside this particular chip. Okay, so if we want to know that how many address lines this particular chip has, or rather let's just jot down the control lines first, and then we'll visit the address lines here. Okay, so here we have it jotted down, and also we can see a picture of the pin diagram of the CMOS 611 IDT 6116 CMOS SRAM chip over here. Okay, so you can see that it has like all the chips concerned, it has two lines, that is VCC and ground lines for the power supply. Okay, and whenever we're supposed to enter data into the chip, okay, or rather store data, okay, then we shall put a logic 0 on the WE bar pin, which just stands for the data storage, or you can also refer to it as a data write pin. Okay, and it's an active low pin indicated by the bar symbol above. Similarly, we have another active low pin here, refers to OE, meaning output enable, or data output, or you can also refer to it as a data read pin. So whenever we're supposed to extract data stored in the memory chip, okay, so whenever there's you can think of it this way, that you have some data stored in the memory chip and you want to extract it out of the memory chip, okay, at that moment you just put a logic 0 on the OE bar pin over here. All right, and in order to control this chip, you have another line known as the CS bar, that's pin number 18, also referred to as the master chip select or chip enable line, which is also an active low pin. So you need to put a logic 0 on this particular chip select line always for the moment that you're working with this particular chip. Okay, now coming to the input output and address lines, okay, let's just go back over here. So as I was talking about the number of address lines, so I said, well, the number of registers is basically given by this term before, okay, that just comes before 8, or that's just written first, that's 2K. So I know that, or rather we know that 2K, okay, or 2KB, 2K bytes basically refers to a total of 2 multiplied by 1024 bytes. okay, and well, this is equivalent to 2 to the power 11, okay, and now this exponent, okay, or the power of 2 that it is raised to, well, this just refers to the number of address lines that a memory chip would have, okay. So there we go. So this is the calculation process by which you can just determine the number of address lines of almost any chip, okay, almost any memory chip concerned. So we might write down that this particular chip, well, it has what, 11 address lines, okay. There you go. And the 11 address lines, but they just range from, well, you can, as you can see over here, this starts from pin number 8, that is A0, and well, this just goes on till you have till pin number 19, that is A10. So it just ranges from, well, pin numbers A0 to A19, okay. And then what happens is that you see, in few cases, I mean, it also has input output lines, okay, which it uses to communicate data, either to accept data from some sort of a device, like for example the 8085 microprocessor, or these pins can also be used to, you know, supply or extract data from the chip. So these are just referred to as the input output lines, okay. So since each register present in this particular chip is basically an 8-bit register, so correspondingly it will have 8 input lines, I mean 8 input output lines, okay, for communicating each the data contained in each of the registers. So it just communicates an 8-bit register's entire data content through 8 input output lines, okay. So you just specify the memory address and you get the data of the corresponding register, okay. So it has, well, 8 input output lines, all right, and this just ranges from, well, IO0 through to IO7. You can just, well, compare it with the diagram over here. So at a particular time instant, by this, you know, information, we can basically guess that, well, at a particular time instant we can access or retrieve information from a particular memory register present in this chip only, okay. So we can just access data from one particular register whose address we just specify on these 11 address lines, okay, and that particular register's data is just supplied by these 8 input output lines, okay, whenever we're reading data from it. And similarly, if we need to store data, then we just give the corresponding register's address, okay, through the 11 address lines that this chip has, and then the 8-bit data that needs to be stored over there is just supplied through the input output lines, okay. And this is just an example of memory write operation, okay. Likewise, we have, you know, various types of other you know, memory chips of different capacities. And well, one more thing I just, you know, left out over here is that now this particular chip, well, as said, it has a capacity of 2 kilobytes, okay. So this is just kilobytes I'm talking in, okay. Now if we just talk in kilobits, then you can basically represent the chip as, well, 2k by 8 bits. So this is the number of bits that the memory chip can basically store. So if you would, you know, obtain this value over here, or multiply 8 with 2, then you're going to get, well, 16k bits, okay. This is the same. So these two notations are they're just equivalent to each other. So these are the total number of bits that the memory chip can store if we just take the entire content of each register in total, okay. So similarly, as I said, we have, well, memory chips of various capacities. So we're just gonna illustrate the same, or let's just take an example of an 8K memory chip here. All right, so that's our 8 KB memory chip, or RAM chip that we're talking about over here. So this is also a static RAM that we are basically, you know, discussing, and it has also pretty much the same sort of control lines that we saw back for the 2 KB chip, okay, previously. And now just let me tell you one difference, okay, that is the 8 KB chip here, well, it has, well, 2 chip select lines that you can see over here. So now out of the 2 chip enable or chip select lines, you can see that, well, one of them is referred to as chip select 1, that is CE1 bar. So this is basically an active low enable line, and the other one that is CE2, that's a chip select 2 or chip enable 2, is basically an active high line that we have, or input terminal control pin that we have over here. Okay, so having two enable lines, this just makes it easier to apply this particular chip, that's the CY6264 SRAM chip, in applications such as memory expansion. So I'll just come to that a little later, but here you can see that now this is basically an 8 KB chip, now meaning 8 kilobytes. So we're again talking in bytes over here, and so basically this chip is also an 8K by 8 bit memory chip. Okay, or you can also call it this is equivalent to saying that it is basically a 64K bit memory chip. Okay, so that is taking all its register bits together in total. Okay, now since it's now we can understand from this particular notation over here, as we did in the previous case, that the next 8 line, the next 8 over here after the K term, that is in this case after 8K, this particular 8 represents the number of register cells. So here we are basically having 8-bit registers. So this chip also has 8-bit registers, and here 8K refers to the number of address lines that it has. So this is basically the number of address lines. Okay, there we go. So in that case, 8K is basically equal to 8 times 1024. Okay, now this is going to be equal to 2 to the power, raised to the power 13. Now this information reveals that this particular chip would have basically 13 address lines. So this power represents number of address lines once again. So the treatment for both the different kinds of memory chip, well, it's not that the treatment is not different at all, except that the chip capacities are just different, and well, they have common notations of their control pins and all, so they're pretty much the same. Okay, so we can just say that it has 13 address lines. Okay, and it will also, since it's an 8-bit, this particular chip contains an 8-bit register, so it will also have 8 input output lines. Okay, so it'll also have input output lines. So the address lines are basically, they range from A0 through to that of A12, so you can just tell it with the diagram. And the input output lines, they range from IO0 through to IO7. Okay, again, you can just compare with the diagram concerned. Okay, so now that we know about what different memory chips that we can actually apply for design, okay, and what are their control lines and what we are supposed to do with them, let's just take a look at how to interface such a chip with the 8085 microprocessor. So in order to illustrate the circuit, I'm going to take this 8 KB chip. Okay, that's the CY6264. Now, since 8 KB chips are used more commonly in industrial microprocessor related applications. Okay, so we're here in order to learn the interfacing of the 8K by 8 CY6264 chip with the 8085 microprocessor. So this particular circuit diagram says a lot about how the circuit should be. So you can see that the read and the write pins of the 8085 microprocessor are basically connected to the CY6264 chip. So this is the CY6264 chip. Okay, there you go. So apart from that, we can see that the multiplexed data bus is connected via the latch. Okay, and the output of the latch just feeds in to 8 address lines of the memory chip, and the data lines, the lower order address data bus, they just feed, you can see via the green wires over here, they just feed it or connect it to the data lines of the memory chip concerned, ranging from IO0 through to IO7. Okay, and the rest of the upper or higher order address lines, you can see that since it's just an 8K by 8 memory chip, so it just has what 12 address lines. So ranging from A8 through to A12, those lines are particularly connected to the address lines. You can see that. So starting from 80 through to A12, they just make up for all the address lines that's just needed in order to connect to the or rather interface the 8085 chip to the memory chip. Okay, and now we can see that the rest of the pins, that is rest of the higher order address lines, that is A15, A14 and A13, they just remain open up till now. All right, and we haven't connected the enable pins anywhere. So if we just thinking of just connecting this particular chip with the microprocessor, well, yeah, it's always easy to make such a system. So we can just ground or just connect to logic 0 the CE1 bar enable line. Okay, that way it just keeps this particular and the CE2 line, that's the enable chip select 2 line. Okay, we just since it's an active high pin, we just connect it to the plus VCC, so that just makes it easy to keep this particular chip always connected to the 8085. But we'll not do so. Why? It's because of industrial reasons. You see, the 8085 has just these 16 lines to interface with any sort of device. So in a commercial 8085 application, it might require for the microprocessor to interface or connect to or communicate with a lot of input-output devices and memory devices as well. So it can also connect to multiple memory chips. So you can also connect the 8085 to multiple memory chips. Okay, and in those applications, it's always required to select a particular memory chip at a time when the 8085 is communicating with it. Okay, so we're gonna illustrate such an example over here. So to enable connection of the 8085 with multiple memory chips, we would like to use a decoder chip. Okay, we're going to use a 3 to 8 decoder. Okay, so that we can just control other external devices, multiple devices, using just the 3 lines that are left open over here. Okay, so to enable the multiple memory chips, okay, we're thought of using a 2 to 4 decoder instead. Instead of a 3 to 8 decoder over here. Okay, so we're just using a 2 to 4 decoder, and this particular decoder takes in 2 binary code inputs, and it can generate a combination of 4 double digit, it can basically generate a combination of 4 numbers. Okay, so depending upon the input over here, if we have the lines I1 and I0, so depending upon 00, 01, 10 and 11, so these 2-digit binary combinations, it can it has 4 combinations, and hence depending upon that, it just selects the corresponding lines. So if you just provide 00 on both I1 and I0, you have the bit or the particular line D0 selected, okay, or rather D0 bar selected. Okay, 01 selects D1 bar, and correspondingly 10 selects D2 bar and 11 D3 bar respectively. Okay, so this is basically the truth table, you could say, of the 2 to 4 decoder that we've just used here in a nutshell. Now there are lots of 2 to 4 decoders that you can basically connect to this system if you just search the net. So you can also as an example, I can suggest some names over here. So you can use 74 HC139 is a good example, and you also have the the corresponding chip of 74LS 155 chip, okay, which is basically a dual 2 to 4 decoder. Okay, that you have two 2 to 4 decoders in a single chip package. Okay, so these are 2 names that I could basically think of right now. So you can just select any or you can just choose any 2 to 4 decoder that you can basically connect, and generally the industrial 2 to 4 decoders available in the market, they have active low outputs, meaning the line that you select over here, so this is basically indicated by the bar symbols on each of the output lines correspondingly. So if you have so if you basically apply this particular code, then the line D0 would have a logic 0 output, okay, while the lines 1, 2 D1, D2 and D3 would be set to logic 1 levels. Okay, so whichever line is basically selected using the selector inputs over here, that particular line just goes to a logic 0 voltage level. So in order to enable multiple memory chip connection, so we can do one thing. We can just, well, connect the D0 enable, or rather let's just think of one more thing. Okay, so let's just do one thing. We can just connect the D0, okay, of output of this particular decoder chip with the CE1 bar, okay, the chip enable that basically is an active low pin over here. There is good enough. And now the other enable line is basically empty. So what do? We just introduce, or rather connect, we have the A13 line empty over here as well. So we just connect it to this particular enable line, okay? Or yeah, if I might draw it somewhat this way, easier. Okay, so now we can, well, communicate with this particular chip comfortably. But what about the concept of multiple memory chip connection? Okay, so let's just introduce another 8K chip into the picture. Okay, so this is the bit of modification you need to put in the circuit concerned to interface with multiple memory chips. So we have, as you can see, 8K by 8 memory chip 1 and 2 as well. So you can see that their data buses, the data lines, are basically shorted with each other, as well as the read and the write controls. Okay, and apart from that, what is most important is that we can see, and also the address lines, as you can see here, well, I can connect them to the address inputs of chip 1 because of space shortage, but I've just written them over here. This should be connected to memory chip 1's address lines A0 through to A12. Okay, and now what is most important here is that, well, how we have interfaced it, interface both of them with the 8085 microprocessor. So here we can see that the 2 to 4 decoder, it just helps select the lines D0 and D1 separately, okay, so that CE1 bar of both these memory chips, okay, 8K by 8 memory chips, they are enabled separately. Okay, if it is enabled for chip 1, it remains disabled for, it just remains disabled for chip 2. And on the other hand, if it remains disabled for chip 1, it remains enabled for chip 2. Okay, so that's vice versa. And the question is that, well, in order to basically interface with an 8 KB chip, okay, we would require at least 13 address lines. Okay, but here we're trying to create a 16 KB chip using 2 8 KB chips. Okay, so this is what we are just trying to do, create 16 KB using 2 8 KB chips. So we have just used 2 8 KB chips, and now if we are supposed to interface our microprocessor with 16 KB of memory chip, okay, then in that case we would require at least 14 address lines. Okay, so we would need at least 14 address lines from the 8085 to be connected to a particular chip. All right, now if we use this many lines with just one chip, then we cannot connect the 8085 to multiple devices, okay, which is frequently needed in industrial grade 8085 applications. So in this case, what we have tried to do over here is that we just realize the same 16 KB of memory space using 2 8 KB chips. So in that case, we use a 2 to 4 decoder chip over here, and also a NOT gate. Okay, so you can see that by enabling or rather setting the A13 address line to, so we're just using the lines 80 through to A13, meaning that's equivalent to 14 address lines. Okay, so we're just having 14 address lines over here. So in one way, we're just employing a NOT gate over here, so that whenever there is, let's say, a logic 1 on the A13 address line, then the memory chip 1 CE2 bar remain, CE2, that's the chip enable 2, remains selected. Okay, so it just selects the memory chip 1, and memory chip 2 remains unselected at this particular moment, okay, because it's just logic 0. And also we can have, there's a logic 0 on the A13 address line, okay, then in that case we'll have the output of the NOT gate set to logic 1 level, which means that the chip number 2 would just be enabled or selected. So whenever this particular, depending upon the corresponding control code on, control level on CE2, CE1 bar of each chip should also be enabled or set to logic 0 voltage level by the decoder. So that way the program needs to be written and the address says basically need to be set so that this happens. So we are basically employing here, as you can see, with the help, with the aid of this NOT gate, okay, we're basically employing 14 address lines. So using 14 address lines, we are actually interfacing or communicating with 16 KB of memory, okay, using both these these two chips together. So this is our chip 1, this is our chip 2. So our memory addresses begin from this particular chip and it just carries on towards the chip 2. So we can use all the chips, both of the chips, entire memory address, and use them as basically as a single chip. Okay, so we're using two chips as one. So two 8 KB chips over here used as one 16 KB chip. So this is what is basically the concept of memory expansion. You can use multiple chips as a single chip. Okay, so this just eliminates the need to have a single chip of a large capacity. So in that case, if it's not available in the market, you can also use smaller chips and create memory that's as large as your application might need. Okay, so having that said, we just wind up our discussion right over here, and we're gonna see you next in the forthcoming tutorials as well. So till then, it's gonna be a short goodbye for now, and keep watching.